Hello, I am Kobayashi from Sony. In this video, we will discuss basic neural network model regarding attention mechanism used as often as convolutional neural networks in recent years. The content in this video is aimed at those with basic knowledge of deep learning. Please view our previous videos covering the basics of deep learning if you would like to learn or review that content. Attention has become a popular technique mainly in the fields dealing with languages such as translation. Because the discussion on the basic concept of attention as used in language processing would become a bit complicated, I will use an image classification task as a means to help you gain a broader understanding of the attention concept. In the latter half of the video, I will go over attention as used in language processing and some popular variations of attention used in language processing. Let's first go over the essence of the idea of creating the attention configuration. In a few short words, attention in deep learning is a mechanism used to represent on what part of input data for some layer to focus, or a mechanism used to create corresponding output for this kind of focused input data. When classifying input images and the current input is an image of a dog, for example, humans will of course recognize that the image is of a dog regardless of what's in the background. We naturally determine the subject of an image by focusing on the main subject without looking at what's in the background. With convolutional neural networks, though, each convolution layer processes the entire image regardless of what is foreground and what is background. Let's look at an example of a network configured with multiple convolution layers and a global average pooling in the final layer to average the features of the entire image. In this network, the final affine fully connected layer estimates the image category. The smaller the area of the entire image taken by the actual subject, the more classification results are affected by the background and other unimportant information. Of course, if the training process is performed using a large amount of data, the neural network learns not to output background features, and so global average pooling is not affected by backgrounds. But it is also considered that learning is difficult because it is necessary to express the processing that focuses on the foreground with a normal CNN. Using attention allows us to configure neural networks to perform recognition by focusing on specific areas in input images. The simplest example of this would be to branch the output of convolution somewhere in the convolutional neural network so that one image is output by two or possibly more layers of convolution. Here we configure sigmoid, which is functioning as the activation function for convolution output, to output a value between 0.0 and 1.0 for each pixel. Sigmoid is a function that stores input values within a range from 0 to 1. So, by using sigmoid as the activation function, a value between 0 and 1 will be output for each pixel. We then multiply these values against the original convolution output. The two additional convolutional layers estimate the areas of focus in the original convolution output. Then the estimated areas of focus are multiplied. Areas near a zero value are multiplied by values near 0, meaning that these values will be near 0 and therefore are not areas of focus. Areas with values multiplied by values near 1 are output as nearly the original value, meaning that these are the areas of focus. Configuring processing in this way results in most of the sigmoid output values that are near 0 not being used in the downstream recognition process. Configuring a neural network to estimate the areas of focus and using the result of which in downstream processing is the most basic example of using attention. In this processing example, only the information on areas of focus is utilized in downstream processing. Because we are using deep learning, we use data-driven training to derive the part of the additional CNN that determines the areas of focus. Next, I would like to discuss the squeeze and excitation type of attention configuration first introduced in the SENet convolutional neural network. As introduced in previous videos, convolution runs multiple filters on input images to generate multiple images as output. Output images represent different features included in different input images. These features are used to determine if images immediately after the input layer, for example, have vertical edges, horizontal edges, dots, or specific colors. With normal convolutional neural networks, all features are used as is in downstream convolution layers. In recognizing images, humans naturally know when to pay attention to color, shapes, or texture patterns. With this said, we will use global average pooling on input images and average pooling on the entire image so that the resulting feature quantity of the entire image processed by a two-layer, fully connected layer. The following figure shows that we are using a one-by-one convolution. We use multiple instances of this to obtain output of the number of dimensions of multiple images from convolution. Then sigmoid is added to derive a value between 0.0 and 1.0, which is used for multiplication operations on each image. The value between 0 and 1 produced by sigmoid is used to determine which features of images output by convolution are areas of focus. We have successfully tested experimentally that we can achieve high performance with only a slight increase in amount of computation using various image classification networks by adding this framework to each convolution unit. The example of attention given at the beginning dynamically determines which areas of images on which to focus. In the next example, we will discuss the use of attention to dynamically determine which specific features in an image on which to focus. This example of attention is used to classify sentences. For this example, we will use a typical sentence classification task of determining if sentences are positive or negative. We can configure a network to focus words at specific locations in the same way that networks determine the areas of focus in images as we just discussed. First, we will use a convolutional neural network or recurrent neural network to obtain the feature amount of each word in input sentences. As we did with processing images, we will use convolution or sigmoid to calculate a value between 0 and 1 used to represent which locations of sentences are the area of focus. The values are then multiplied by a feature vector output from each word. The result is averaged with the entire sentence or totaled, which is then used as the basis to perform the recognition. This configuration enables a neural network to estimate the specific words of focus that allow the final estimation of whether a sentence is positive or negative. In this example, the neural network can determine that a sentence is positive by focusing on only the word exquisite in the sentence. Now let's go over a typical use of attention often used in language-related tasks. Before we discuss using attention, let's first take a look at the basic neural network used to translate input sentences via LSTM in a recurrent neural network. I have discussed recurrent neural networks in LSTM in past videos, so please check those out. The top part of the network used for LSTM-based machine translation extracts features from the first word via an encoder. Features of the next word are extracted from the next word and the features of the first word. This process is repeated to extract features from all words. The result of this processing is that the LSTM output vector, once the last word is reached, retains features of the whole sentence. The bottom decoder is used to take the feature vector obtained by the encoder to generate a translation of the original sentence. From the first vector, the first word is output. Then a feature vector is generated from the first vector and first word to produce the second word. This process continues for all words. This process is similar to that of a person who reduces the content of a sentence that they hear to a concept and then recreates a sentence based on this concept. However, when a person actually translates content that needs to be translated accurately, I would assume that the process involves finding a corresponding match of each word in the source language. In translating this sentence, for example, first we have the subject, which is hamburger. Then we have the Japanese for in this restaurant, which has not been translated yet. As the process continues in this way, the sentence is translated more accurately by linking each word in the source to a word in the target. Here, we will use attention to focus on the first word that should be translated and output this first word. Based on this output, the neural network determines the next word of focus in the original sentence and then outputs the next word. This process is repeated to perform the translation process. There are multiple ways to implement attention, so I will introduce the easiest way for the sake of discussion. The attention configuration here will determine what part of the input sentence on which to focus as the network outputs each word. While a little complicated, let's look at actual operation as we continue to discuss. To estimate the first word in the translation, inner product of initial vector of the decoder and the feature vector of each word, which is the output of the encoder, is calculated. Attention produces a score for each word whereby larger scores indicate the words of focus. Then a softmax calculation is performed on this score. This operation converts to a probability expression in which the sum of score values is 1. This represents the location of focus in the input series. In this case, this is the word hamburger. The softmax value is multiplied by the feature vector output by the encoder at each time step in the process. The feature vector for each word is added to at each dimension. In other words, a weighted sum operation is performed on the feature vector so that words with higher degree of focus have greater impact. Then the first word of output is derived based on the combined features and the LSTM output. This process repeats to derive the next word in the sentence. The next word is determined by calculating the inner product of the output LSTM for the previous time step and the features at each time step of input and then obtaining the softmax value. In this case, this is still the word hamburger. A weighted sum operation is performed on the feature vector using the softmax weight, and then this is concatenated with the LSTM output to output the next word. This process repeats until the entire sentence is output. While it seems complicated at first, we basically have a framework in which the area of focus in the input is calculated for each word of input. In addition, a feature vector is obtained so as to increase the impact of the area of focus. This is all used to obtain each word of output. Now that we have covered the simplest method of implementing attention, let's now look at a slightly more involved process to separate the features of a word in the source into a key and a value. In this case, we have a query vector and a key vector used to determine the word of focus. The inner product of these vectors is obtained to perform the calculation to determine the word of focus. The softmax value is multiplied by the value vector instead of the key vector to obtain the weighted sum value for each dimension. Separating feature information into a key vector used to determine the point of focus and the value vector that represents the value ultimately used enables us to create the neural network configuration that produces better expressiveness in the target language. Let's now talk about the roles of the query, key, and value vectors. The key and value vectors represent what answer to provide in response to what query for each word in the source. The query vector represents the type of query in the target. Once the query vector is input, the inner product is obtained for each key using the query to then obtain a degree of similarity. Because of this, the largest key vector that is most aligned with the query will have the largest value. Then, a value corresponding to the key is output. The actual inner product will be a probability obtained by adding softmax to produce a value of 1. Then, the value is weighted based on this result. The resulting process obtains a key value that aligns with the query. Next, let's talk about self-attention used in language models. In the previous example, attention was configured to use the query key and value vectors to create correspondence between two series of different sequences. With self-attention, the query key and value are used to extract features from a single series. For example, the meaning of a word depends on the meaning of other words in the sentence. This can be seen when a sentence contains a negation or modifier. In this sentence, the word dislike is negated by the word don't. Self-attention enables operations that determine the features of one word by using other words as reference. More specifically, the query, key, and value vectors are created for each word in the input when extracting features of a sentence. Taking the word dislike at the third position, for example, an inner product calculation is performed on the query vector for dislike and key vector for all words, which is then summed using softmax to derive a probability that equals 1. Then we would expect the model to assign a large value to the word used to determine features for dislike, which in this case is don't. This weight is multiplied by the value vector and used to perform a weighted sum operation on the current word. For example, the model can express a negation by focusing on the second don't to characterize the word dislike. Self-attention is a framework whereby the neural network updates itself with the results of using attention. This is different from the use of the source target attention used to create correspondence between two different series. Using self-attention enables a framework whereby features of one area of focus are determined by focusing on another area of focus. This self-attention is increasingly used in image processing. We can take the output of convolution, for example, and create query, key, and value vectors using one-by-one convolution. Each pixel, such as one upper left pixel, is equivalent to a word in the previous example. The vectors as shown by red border are the query, key, and value vectors for each pixel. In this example, self-attention is used to determine which pixel in a 7x7 pixel area on which to focus and how to determine features of each pixel. First, the inner product of the query vector for the upper left pixel and all other key vector pixels is derived. From that, the softmax value is then obtained. The result of this is the determination that the features of the upper left pixel should be determined by other pixels. Then values of all pixels are weighted using the softmax result as the weighted sum operation is performed. The processing as described up to this point is performed on all input pixels. The result of all of this processing is used to perform a weighted sum operation on the original input to derive an output. Using self-attention for each pixel like this has been effective in challenges with changing results, such as when there is significant distance between objects in the image. This technique has also been particularly effective when such positions are too far to be expressed with convolution or when there are too many variations of the position. With that, I have showcased some attention frameworks consisting of architectures used to perform language and image processing tasks. Some might think that using all input with a fully connected configuration is the best approach even if not using an attention framework. However, a fully connected configuration results in too many parameters, which could result in overtraining from a limited dataset. Using an architecture like attention with dynamically changing connections to express loose connections and local neuron connections achieves a stable training process and high performance from limited data. For example, convolution is a function with limited expressive power by loosely coupling compared to affine. Refining the number of parameters and expressiveness to be just sufficient for the specific task ultimately results in better performance. Attention is quite a broad concept with many variations. The examples presented here are just a few typical examples. For example, attention can also be used to select values to be included in gated cell states as well as output values regarding LSTM configurations as introduced in the previous video. As you now understand, dynamically changing neural network connections according to the data entered by using attention to dynamically change the point of focus has broad applicability. I encourage you to try designing attention configurations suitable for your purpose. In future videos, I would like to discuss popular neural network configurations that incorporate attention for language-related tasks as well as how to implement such configurations in Neural Network Console.